This is an introduction to the Java Persistence API, or JPA, and in particular Hibernate. Complex applications make frequent use of an underlying data model. In development, a lot of effort is put towards mundane tasks of coding CRUD, create, retrieve, update, and destroy. Data abstraction layers and frameworks have freed developers from needing to worry about loading, persisting, and managing data, keeping them closer to the application layer. The Java Persistence API, or JPA, is one such framework. We'll give an introduction to the basic concepts and use of JPA through Hibernate. JPA is a framework for managing relational data. It provides a data abstraction layer between the database and POJOs, or plain old Java objects. JPA and similar tools are often referred to as Object Relational Mapping, or ORM frameworks. As we will see, JPA allows you to annotate your Java classes to specify a connection from an object to a table and from an object's member variables to a table's column values. Once this mapping has been defined, the framework takes over the responsibility of managing the connection between a Java object and a table record. It relieves you, the programmer, of the need to write boilerplate JDBC code to connect to a database and make queries. The API is defined in the javax.persistence package and provides many interfaces for querying and managing data. It also provides a special JPQL query language, which is similar to SQL, but instead of querying a database, we can query a Java object instead. JPA is actually built on top of JDBC and is quite mature and stable. To illustrate the differences between JDBC and JPA, consider the enrollment database that we designed before. There was a one-to-many relationship between the students and the emails. One student could have multiple emails. And there was a many-to-many relationship between the student table and the course table, realized by the join table enrollment. To interact with this simple four-table database in JDBC, we would need to manually load the driver and to make our own connections. We would need to formulate our query and process every result and every record. If we wanted related objects, we would need to write a join query or make additional queries. This represents a lot of coding, debugging, and testing just to write some standard boilerplate CRUD. Let's take a look at a small example. Here we have a student class and a course class to model the tables in our database. In this demo class, we make a connection to the database to load a particular student record. We have our NUID stored as a string, along with our database credentials. We then proceed with the boilerplate CRUD. We load our driver, we make our connection, we formulate and execute our query, and process the results. Furthermore, we have to formulate and execute additional queries to retrieve the student's email records and course enrollment. And we have to clean up after ourselves. There's more than 100 lines of code to simply retrieve data from four tables. Now imagine a more complex application with dozens or hundreds of tables. Furthermore, we have to write methods to persist the data, inserting, updating, and deleting records for every one of these tables. That represents a lot of work. How is this different in JPA? First, to use JPA, we need to annotate our Java classes to map them to tables and columns. Once we have fully annotated our classes, JPA takes care of the boilerplate CRUD for us. JPA provides an entity manager that handles the loading and the persisting of data to the database automatically. Instead of formulating queries towards the database, we can use JPQL to make queries to Java classes. We can now focus on our Java objects instead of worrying about interacting with the underlying database. We'll cover the basic usage of JPA in several steps. I'll demonstrate how to set up a project and to use JPA. Then we'll cover how to configure the project by defining a persistence unit. Then we'll examine some classes and how we annotate them to turn them into JPA entities that can then be managed by JPA. Finally, we'll query our entities out of the database using an entity manager and JPQL. JPA is only an API specification, similar to JDBC. We'll need an actual implementation of the API. We'll do this by using Hibernate, which is a popular implementation created by Red Hat. It is free and open source, released under a GPL 2.1 license. There are alternatives such as OpenJPA, which is an Apache project, as well as alternative ORM frameworks such as Juke. We'll take a look at getting started with Hibernate. Here's Hibernate's main website. The first step is to download the Hibernate code available on their website. I've already downloaded the latest version here. Alternatively, you could set up a JPA project using Maven or some other dependency framework. The download comes with a lot of artifacts, but you'll only need a few of the jars in your actual project. I've already set up this project to use JPA. I've only included the jar files that are necessary. To configure our project, we need to define a persistence unit. A persistence unit is a data source configuration which includes the necessary information to connect to a database, including a URL, username, and password, as well as the driver. We do this in a persistence.xml file in our project. Let's take a look at the persistence unit in our project. Here's our persistence.xml file. I've only defined one persistence unit, but you could have as many as you want, connecting to different databases on different servers or with different configurations. My persistence unit is named Big Red. In this unit, we've defined everything necessary for JPA to make a connection, including specifying the driver, URL, username, and password, which has been redacted. Note that in this file you can also define the object relational mapping if you wish. However, we'll use annotations to do this. The next step is to annotate our classes. For JPA to manage a connection between a Java object in memory and a record in the database, the class needs to be a JPA entity. The entity annotation turns a plain old Java object into a JPA entity. We should note that JPA requires entities to be serializable. The table annotation is used to map a class to a particular table in the database, while a column annotation is used to map an individual member variable to a column in that table. The ID and generated value annotations can be used to specify the primary key as well as how it is generated. In our database, we used auto increment to generate all primary keys, which corresponds to the auto generation type in JPA. Let's take a look at an annotated version of our student class. Here's our student entity. We've used the entity and table annotations at the top to specify that this class is a JPA entity corresponding to a table named student. We've made the class serializable with a default version ID. We've also annotated every member variable. The ID variable is our primary key, which is auto-generated, and corresponds to the column named student ID. Likewise, the NUID and first name and last name variables have been mapped to their columns in the database. In addition, we can specify whether or not a column is nullable. The default is true. Though the variable names match the column names here, that is not necessary. In fact, the primary column is named student ID, but our variable in our Java class is just ID. Other annotations can be used to define relationships between Java classes. Each of the four basic types of relations, one-to-many, many-to-one, as well as one-to-one and many-to-many, are supported. These relations only work in one direction. That is, if we define a one-to-many relationship from class A to class B, the inverse many-to-one relationship from B to A is not necessarily defined. We would have to define the relation in both classes in order to have a bidirectional relationship. The many relationship is realized in Java using the set interface, defined in the standard collections library. Furthermore, the join column annotation is used to define which column should be used as a foreign key in the relationship. Many-to-many relationships require a join table specification. If there is information in the join table besides the two foreign keys that connect the two records, you may need an intermediate join object in your Java code. Otherwise, you can treat it as a pure join table and forego the extra Java object. To illustrate, let's look at our examples again. In the student object, we have a set of emails. We've defined a one-to-many relationship from the student class to the email class. The join column is specified as the student ID because the student ID is the foreign key used in the email table. In the email object, we've defined the inverse relationship, a many-to-one relationship to the student object. with the same join table. The join column is the student ID foreign key, which is specified in both directions. Likewise, we have a many-to-many relationship from the student object to the course object. Here we've specified the join table as well as two foreign key columns. Since we're in the student object, the join column is the student ID, while the inverse join column is the course ID. In the course class, we would need to reverse these. But in fact, we have not defined the inverse relationship in the course class. It doesn't own a set of students. Therefore, there is no bidirectional relationship between these two objects, as there was between a student and an email record. One consequence is that we would not be able to produce a roster of students for a particular class. We would have to change the design of this object to do so. Moreover, we have not defined an intermediate enrollment class corresponding to the join table. One consequence of this design choice is that there's no way to tell which semester a student actually took a course in, nor do we have access to the enrollment table's primary key values. If we needed these particular pieces of information, we would need to implement an enrollment join object. In our examples, you might have noticed that we sometimes specified a loading strategy using the fetch property. By default, all entities are loaded from the database lazily. That is, JPA does not actually query the database until our program actually needs the data in the object, say to access it to use it in a calculation or to print it out. Lazy loading is potentially more efficient in that if you never actually need a particular column value, JPA will not waste the resources to load it from the database. An alternative is eager loading, which fetches a related entity immediately when the referencing entity comes into the scope of the entity manager. In our example, if we were to load a student from the database, all of the associated email records and course records would also be loaded, even if we never needed them. Say if we just needed to list a student's first name and a last name. This is potentially more expensive, but a better strategy if the entire entity and related entities should be loaded, as it avoids multiple queries to the database. Sometimes our objects may have member variables that do not correspond to database columns. We can specify that a member variable has no connection to any column using the transient annotation, the antonym of persistent. This lets JPA know that the member variable should be ignored. If we fail to annotate a member variable in an entity with either a column or transient annotation, it will result in a runtime exception as JPA doesn't know what to do with the member variable. In addition, it's important to understand that JPA works through reflection. That is, it generates and injects code at runtime. In general, this comes at a cost and efficiency, but leads to faster development time. Another side effect is that all JPA entities must have a no-argument default constructor. You can make it private if you don't want to allow your code to use it, but it must be present for JPA to work. It's also important to understand that Hibernate is a particular implementation of JPA, and also provides some additional non-standard functionality. Everything that we've covered so far is standard JPA, but you may find some tutorials using Hibernate-specific functionality that you should generally avoid. Recall that JDBC uses checked SQL exceptions everywhere. JPA, however, has fixed this design flaw and only throws runtime exceptions. Still, it's good practice to try catch them. There are a lot more annotations and features provided by JPA that we'll not cover here. Once all of our classes are annotated, we can now use JPA to actually query objects out of our database. We have to initialize an entity manager factory, which automatically loads our persistent unit. From this, we can create entity managers and formulate transactions and queries to it. The entity manager can be used to load, update, and persist JPA entities. We can also roll back or commit transactions. As with JDBC, once we're done using the entity manager, we need to close it. We'll illustrate with a few examples. Let's first write code to query all students out of the database. To start, we'll need an entity manager factory, which will load our persistence unit. We'll also need to create an entity manager. I'll add a general try-catch block, in which I'll open both of these and close them in a finally block. The Entity Manager factory is loading our big red persistence unit. Let's formulate our query using JPQL. Instead of querying a table in the database, we can make queries to our JPA entities. In this case, we want to select all student entities. Here, student is referring to the student object and not the student table. JPQL is a bit different from regular SQL. This will work, but student is referencing the student object and not the student table. As a consequence, we will use a shorthand form of this. From student is all that is needed in this case. We can now use the Entity Manager to create a query and get a result list. First, however, we'll need to get the Entity Manager's transaction and explicitly begin it. If we were writing to the database, we'd also have the option of rolling back the transaction or committing it. The query object I've used here returns a raw list type, which forces us to do an explicit typecast. Alternatively, we could have used a type query to guarantee the type safety. A typed query is parameterized, and so it returns a parameterized list. We'll go with that solution. Now let's try to simply print each student to the standard output using the student object's toString method. And let's run our program. It didn't work. The exception indicates that a collection, in this case the emails of the student entities, failed to lazily load. To understand why, let's look at the student class again. First, notice that the emails are stored both as entities and as a list of simple strings. The list of strings is built in a getter, so we've marked them as transient because they don't actually have a direct correlation to the database. Also, the fetch strategy is lazy, so that they are only loaded if we attempt to access them. However, over in our demo code, we roll back the transaction and close everything before we actually print it. Thus, the email records were never loaded. Since we close our Entity Manager before we ever access the email entities, the email records were never loaded. Thus, when we attempted to access them by printing them in the standard output, the exception resulted. We could move this code to inside the try-catch block before we close the Entity Manager. And it would work. Alternatively, we could change the loading strategy. And it would also work. Now the demo code runs. What if we only want a particular student, say Tom Waits, whose NUID is given here? Let's create a new demo class and repeat some of the basic outlines in this example. Here we only want one student, whose NUID is equal to this string down here. We can change our query to only get one student. I've set up a parameter. In JDBC we would use the question mark character, but in JPA I can use named parameters, indicated by a colon. I can then set the parameter. Here I'm only getting one result, so I use getSingleResult instead of getResultList. And and we've successfully loaded a single student. Now let's write code to demonstrate the persistence of data. We'll create a student, give them some new emails and a new course, and enroll them in that course. First, let's create the student. Now let's start the transaction and persist it. This saves it to the database. But note we only gave it the NUID, the first and last name. The object in memory at this point would not have the student ID that was auto-generated by the database. To get it, we can refresh it. We can now do the same thing with the student email records. The second parameter in the constructors here is the student. Recall that there's a bidirectional relationship. So we've associated the student with the email record, and we need to do likewise with the email record to the student. And now we can persist them. Let's create a course as well. If everything's gone well, then we should go ahead and commit our transaction. And let's run our program. Everything ran. Let's go ahead and go back to our first demonstration and see if it worked. And the new student record has been successfully inserted and persisted. Updates and deletes likewise can be performed through JPA. To review, the Entity Manager provides a lot of other functionality. You can load an entity from the database, persist to it, detach the entity from the Entity Manager, which effectively removes the connection between the Java object in memory and the record in the database. You can sync up the database with all managed entities. You can delete entities from the database, and many more. Again, JPA provides an SQL-like query language called JPQL. You can still execute native queries, that is, regular SQL queries, using the native query interface. JPA provides several potential advantages over JDBC. First, it's closer to object-oriented programming. You don't have to worry about the access to the underlying database. You can deal exclusively in Java objects. It's portable across application servers and persistence products. It can be configured to provide connection pooling, caching, and many other features. Though there are some disadvantages. There is a slight performance hit due to the use of reflection and auto-generated queries. JPA tends to be a resource hog, and a well-designed JPA entity needs a clean object database mapping. If you don't have a clear mapping from a Java object to a database record, then the annotations can become quite complex and difficult. All of the code as well as additional issues and topics are available on the webpage.